Okay, this is number 11 on 2.1, and I'm glad somebody asked this because it's actually kind of a question for myself as well. So, anyway, we have a census company with the figure that 10.1% of all babies are born with a low birth weight. An obstetrician wants to know if mothers between the ages of 35 and 39 years old give birth to a higher percentage of low birth weight babies. She randomly selects 280 births for which the mother was 35 to 39 years old and found 30 low birth weight babies. So the first thing they have you do is compute the expected number of low birth weights, and that's just taking the 10.1% and multiplying it times the 280. And then the expected of not low birth weights, which is just 280 minus the low birth weights. Okay, and so the student got that. The obstetrician's question at a 10% level of significance, using the chi-square goodness of fit test, state the null and alternative hypothesis for this test. So the null is just that the proportion is still is 10.1. The obstetrician thinks that it's higher. And so the alternate hypothesis is that it's more. What's kind of confusing about this problem is just seems like a straight up chapter 10 proportion, one sample hypothesis test. And furthermore, it's not clear to me that the goodness of fit test can be used because we have the greater than. The obstetrician clearly wants to know if the low birth weight babies is more than 10.1%. So we have the greater than here. But in goodness of fit, you're doing not equal to, right? Your assumption is that the proportions are all equal to whatever your default assumption is. And then you're checking to see if the proportions are not equal to. So they want us to use technology, right? StatCrunch. I use StatCrunch to find the p-value for this test. This is how you actually do it. It's kind of weird. So I'm just going to open up StatCrunch. And let me get set up here, a little side to side. Okay, so what we're going to do is, like all the other goodness of fit tests, we're going to have an observed column, or expected. I guess it doesn't really matter which order we put them in. Expected and observed. So the two proportions for this test really are the low birth weight babies. So we expect 0.28, and we observe 30, right? And the non-birth weight babies, or the non-low birth weight babies. So this is we expect, if the default assumption is correct, we expect 251.72 non-low birth weight babies, and we observe, let's see, 280 minus 30, that's 250, right? And so now we can do the goodness of fit test on these two proportions, okay? But they're really just complementary proportions, which is kind of different than most of the goodness of fit tests that we run. So here's a chi-squared. We have the expected and expected. The observed and observed. The expected and expected. And then we just get my big head out of the way and compute. Okay, and this is where they get that p-value of 73% there, 73.3%. Okay. Now, what does this mean? Well, the conclusion is that we're testing at a 10% level of significance. So this is well above 10%. So we do not reject the null hypothesis. There's not sufficient evidence. On the second one, they ask us to rerun the same hypothesis test, but this time use technology to compute the p-value. They want us to do it with the z-test for population proportion. This is what I was saying is what my intuition would be for doing the problem all along. Just going to They call it the z-test because it uses the normal distribution with summary. So this is just the number of successes, 30. Number of observations, there were 280 in the test. Our hypothesis is 10.1%. And we want to see alternate hypothesis is that it's more than 10.1%. So we hit compute there, and then we just get that 36, 30 there, which is interesting. So this is half of that. So I'm gonna this is a good. The reason I didn't throw the problem out was because it raises a really interesting question, and I'm going to try to get somebody who has a deeper understanding of stats to explain why we would, want to use the goodness of fit test and if it's even applicable in this situation. I had the feeling that this is double this just because the goodness of fit test is two-tailed, right? Whereas this is just one-tailed. So there's double the probability of getting it wrong, right? So yeah, I hope that helps a little bit. Just get through the problem. I guarantee this problem won't come up on quizzes or tests. Okay, it's really this question raises lots of more questions than it is meant to test knowledge. Oh yeah, same thing here. We reject the null hypothesis. There's not sufficient evidence because this is well above 10%. I just reject the null hypothesis. No, sorry, we want to do not reject the null hypothesis. There is not sufficient. Sorry. Do not reject the null hypothesis. There's not sufficient evidence. All right. Have one more check. So I hope that helps a little bit on this problem. It's a tricky problem, but I'm glad somebody asked it.